So this video will be about the 5 different types of atomic models that we've seen throughout the years. We're going to take a look at each one, identify some key elements of each model, and then we're going to compare them to the other models. So let's begin. The first atomic model that we had was Dalton's atomic model. Came around in 1803. So in this model, he considered atoms to be dense spheres of matter. Each atom was different from one another. So that's what we're seeing here. We're seeing oxygen, hydrogen, and nitrogen. All of them are dense. All of them are different from one another. So each atom, of course, is different from one another. Now, at this time, in 1803, we didn't have any information about the subatomic particles. So he didn't know anything about protons, neutrons, or electrons. Only thing that we knew was that they were small, dense, indivisible, and each one was different from one another. Then we have Thomson's atomic model. In the 21st century, I call it the Oatmeal Raisin model, but originally it was called the plum pudding model. This came about in 1904. Now, in 21st century, most people really don't know what plum pudding is. So we go with oatmeal raisin because essentially it's a dense matter and it has different components inside of that matter. So we'll see that here. So atoms were still considered dense. In this case, we're going to talk about nitrogen. But now we have positive and negative charges found throughout the atom. So you see them being drawn here. We have 7 green protons and we have 7 red electrons. So overall, even though there's positive and negative charges, the overall charge of the atom is neutral. So this is going to be very important moving forward. So as you can see here with the equation, we have 7 protons plus 7 electrons gives you a charge of 0. When the charges are equal to one another, protons and electrons, you're going to have an overall neutral charge, which means no charge whatsoever. Then we have Rutherford's atomic model. This was extremely important and extremely changed the game, if you will, changed the whole game of chemistry. So the big discovery here was the nucleus, and this came around 1911. So Rutherford discovered that atoms were mostly empty space. This is revolutionary compared to the previous 2 atoms. The previous 2 models showed that the atoms were dense, but now Rutherford discovered that they were mostly empty space. He also discovered that atoms contain a dense, positively charged center, which he named the nucleus. In addition, he discovered that the electrons had to be dispersed throughout the rest of the atom in that quote-unquote empty space. So here you see 79 electrons surrounding a gold atom, but notice that they're not interacting with the nucleus. Now, the one thing that Rutherford was not able to pinpoint was the exact location of the electron. The only thing he knew was that they're there, that they exist, and they travel around the nucleus within a certain distance. Now, he discovered all of this through his famous gold foil experiment. So, if you're not sure about the gold foil experiment, you'll have to look it up, find information about it, because it breaks down exactly how he discovered the nucleus. Very important to chemistry, that experiment. Now, the Bohr model, on the other hand, this came about 2 years later, and this time we have something called electron shells. Big difference. So instead of the electrons just traveling about freely, they're traveling around designated paths called electron cells, and they were traveling as particles. During the time, there was a big debate on whether or not electrons and light moved as waves or as particles. About half the scientific community said they traveled as waves. The other half said they traveled as particles. Einstein split the middle and said that they were both. People were very upset at the time at Einstein for that. But Bohr decided that they moved as particles, and he took that idea and ran with it. So we still have the nucleus, still mostly empty space, but now we're noticing that the electrons are in electron shells around the nucleus. In this case, we have 3 shells. So each electron shell is discrete, which means it can only hold a specific amount of energy, no more, no less. So electrons can't be in between shells, can't be in this space here, can either be in energy level 1 or energy level 2 or energy level 3 and so forth. There's no half energy level. So you're either in the energy level or you're not in the energy level. Also, these shells can only hold a certain amount of electrons. In this case, energy level shell number 1 holds 2 electrons, 8 electrons in the second energy shell, and the third electron shell can hold 7 electrons in this case. So when you add them all up for chlorine, you get 17 electrons total. So overall, chlorine is still neutrally charged because you have 17 electrons and 17 protons. Okay, now, this is the ultimate picture, and the ultimate and the most current model. That's the quantum mechanical model. So, at this point, 10 years after the Bohr model, we saw that electrons display waves, wave-particle duality, as they travel around the nucleus in designated orbitals. Okay, so what you're seeing here is you're seeing for the first time in 2015, Fabrizio Carbone, finally was able to photograph electrons as particles, which you see here, and also as waves at the same time. Electrons that travel in the red part of the spectrum have low energy. Notice that it's lower than the purple energy. And also the wavelength is very long, which means the particles are separated from one another. But as you add more energy, the wavelength gets shorter, the particles get closer together, and you get more energy. This is something Einstein predicted over 100 years ago. So in 2015, we were able to photograph it and see wave-particle duality simultaneously for the first time. Very cool. Now, as it turns out, both light and electrons exist as waves and particles at the same time. So this is proven, confirmed, very cool, and it's the foundation to the quantum mechanical model. All right, so inside this model, we see something called orbitals, like I mentioned earlier. Orbitals are patterns of electron density. So what it's really showing you is the statistical probability of finding an electron in an atom. So what we're seeing here are several different orbitals. Everywhere in this blue, in this case with the s orbital, this is where you're most likely to find an electron. These are p orbitals. These are d orbitals. Lastly, we have f orbitals here. So each orbital holds 2 electrons that travel in opposite directions. And each orbital has a different 3-dimensional shape. So as we see here, these orbitals are not flat, but they're 3-dimensional. Notice that there's 3 axes, y, x, and a z axis along the back here. So that's the basics of the different atomic models. Feel free to go back and rewatch this video at your leisure, so that way you have the differences well understood.